Cool, thank you. Thanks for troopering on through the whole week. At this point, reproducibility has kind of become like motherhood and apple pie. But I want to talk about why we need to care about it. And the first thing I want to do is step back and ask, how confident we really are in the way that we do science. How many of you know about phrenology? So, phrenology it actually started out as sort of like real scientists. So like Franz Gall, who was like the first sort of, phrenologist, he was actually like a serious neuroanatomist and somehow got confused about it makes no sense. If you know anything about brains, it's like jello. There's no way that like if a part of your brain grows, it's going to push out on your skull. But nonetheless, they thought that, parts of your skull, the size of parts of your skull would reflect the strength of particular brain faculties. And so what they would do is they would bring people in and feel in their skulls and say, oh yeah, you have a big wisdom bump. You must be very wise. And the person says, yes, I'm very wise. And I said, okay, my theory is confirmed. And so of course, what we're doing is so much more scientific than that, right? We would never get stuck, sort of making those sort of conclusions that, sort of lie primarily on the assumptions that we walked in with, right? But if you have not been living under a rock for the last few years, you know that there's been increasing concern about exactly this, right? About the fact that a lot of what we think we're doing as scientists may not really be much better founded than what the phrenologists were doing. And we see this not just, it sort of started in psychology, but we've actually seen it across many different parts of science. And, The Economist had this thing, How Science Goes Wrong. We've seen it in cancer research. And I don't know how many of you are familiar with John Ioannidis' paper, Why Most Published Research Results Are False. We'll come back to that in a moment, but that one I think lays out the case probably better than anyone else. So why does it matter? What's at stake here? So here's an interesting place where a lot was at stake. So how many of you are familiar with this? So this was a paper published in American Economic Review back in, I forget when it was published, some time ago, right, 2010. Actually, it was published before that. Yeah, I guess in 2010. And basically they did some analyses of the relationship between growth and national debt, and basically tried to make the argument that national debt was a really bad thing for economic growth. And this paper was amongst the strongest foundations for like all the austerity programs that were put in place in places like Greece, after the financial crisis, 2009-ish. And it turns out that their first mistake was using Excel, and their second mistake was putting an incorrect number in their formula, which happened to leave out like one of the strongest counterexamples to their theory. And they, fortunately, they put their data out. Somebody went in, these people from UMass looked at the data and said, hey, look, you screwed this up. So basically, the arguments for economic policies that ended up making a lot of people's lives really miserable turned out to be based on an Excel spreadsheet error. So I left out my never use Excel slide here, but you guys don't need that anyway, right? So I want to argue that neuroimaging is, in many ways a perfect storm for all of the things that can sort of drive your reproducibility. And so John, in his paper, how many of you have read this paper? Okay, I definitely would assign this as like, take-home reading. So basically, he lays out the argument, and I'm going to come back to the statistical argument that he lays out in a bit, but he sort of walks through what are the things about a particular field of science that would cause it to be more likely to do irreproducible research, or more likely to have false positive findings. And if you look at these, almost all of them are true of most kind of hot areas of science these days, but I think particularly in neuroimaging. So the smaller the studies conducted, we'll come back to that in a bit and talk about how big are studies these days. It turns out they're not really big enough. The smaller the effect sizes, and I'll show you some data on how big effect sizes are in neuroimaging. They turn out to be smaller than you might think. The greater the number and the lesser selection of tested relationships. So we're doing 200,000 hypothesis tests in each analysis. We might do many of those analyses for a particular study. That's a lot of things being tested, and often a lot of selection, where we sort of sub-select things to further investigate them. The greater the flexibility in designs, in particular analytic modes, you all know that, right? You open up NiPipe and you can see all the things that one can do to an imaging data set. We have a ton of flexibility. Not so much a greater financial interest, but certainly maybe prejudices. And the hotter the field with more scientific teams involved. And certainly I think we've seen that certainly in parts of neuroscience. Okay, so what are our alternatives? One alternative is to like throw up your hands and quit, right? We don't want to do that. So the other alternative is to try to make it better. And so Chris and I started a center a couple years ago with funding from the Laura and John Arnold Foundation to basically try to do this, to try to come up with ways to help improve how we do neuroimaging in particular. And so I'm going to what I'm going to do is walk you through some of the things that we're thinking about, how we might improve neuroimaging analysis in the context of making the work more reproducible. But first I want to kind of step back and talk about kind of how I think about this stuff more generally. Does anybody know what this is? It is a commercial paper cutter. I worked in a print shop when I was in high school and had to operate one of these things. It has two green buttons right here. Why do you think it has two green buttons on it? Exactly. So somebody designed this machine. They anticipated that someone would be stupid enough to put their hand in there and hold the paper while they pressed the one button, right? So they made it so that people have to hold the two buttons. It makes it real. I mean, you could presumably like do something stupid, but it's hard to cut your hand off with this machine, right? And so more generally, when we think about design, we think about sort of building things so that people use them correctly, right? You would never build a teapot like that because it would afford bad usage, right? So we want to think about how do we design things, and in this case we're thinking about how do we design our scientific enterprise more generally, or how we analyze data more specifically to afford people doing the right things. All right, so there's a nice book called Nudge which talks about the idea of choice architecture. So choice architecture is the idea that whenever people go into a situation, if you've designed the situation, you've implicitly sort of driven them towards some things and away from some things. So defaults are the best example, right? If I open up SPM and I analyze my data and the default threshold is p less than 0.001, it's very unlikely that people are going to change that, right? Similarly in FSL, they use a different default, 0.01, right? And that's a really strong driver of people's behavior. And we know there's lots of work showing how susceptible people are to the power of defaults. There's lots of other ways that they talk about what they call nudging, basically driving people towards doing the things that you want them to do. But I think the two most important for us to think about are, one, defaults, sort of giving people the best possible way to do things, and then both expecting them to make errors, because people make errors, we're humans, and then doing whatever you can to prevent those errors. And we'll talk about that in a number of different contexts. So what I'm going to do now is talk about what are some of the specific threats to reproducibility in neuroimaging, and probably the biggest is statistical power. This is a paper published a few years ago that focused on both structural imaging and animal behavior lesion studies, and basically showed that the modal level of power, statistical power in all these studies was less than 10%, really bad, right? So Sean David gave us some data from an older meta-analysis that he had, and then we worked with Tal develop some code to automatically extract sample size data from Neurosynth, and then somebody in our lab went through and manually annotated those. So we have I think it's about 500 studies since 2010, and then there was on the order of 600-700 studies prior to 2010 where we have manually annotated sample sizes. And what you can see is that the sample size has been going up over time. This is the median, and it's now in 2015 it was at 28.5. And so the question is, what does that tell you about statistical power? And there's lots of ways you could try to sort of ask this question. We've done it in a few ways, and this was an analysis that Joka Durnas from my group did, kind of saying what would your power be for like a reasonable sized cluster in a reasonable sized area, and in particular, because we don't know necessarily what these studies are powered to do, but we can ask, given their sample size, how big of an effect size were they powered to find? And that's what the rightward panel is. And the idea is that the bigger the study, the smaller the effect size you're powered to find, right? And the median effect size that we're powered to find is 0.75. Now, if you, there's this kind of rule of thumb, right, about effect sizes. This is the unit of effect size here is Cohen's d, which is basically like the effect in terms of standard deviations. And the rule of thumb is that a small effect size is like 0.2, a medium is 0.5, and a large is 0.8, right? So basically this is saying that you're basically powered to find a large effect with the average or the median study in the literature. And so the question is that a reasonable thing? You might think that fMRI effects are huge, right? In which case, that's great. We're powered to find reasonable fMRI effects. So it's hard. The problem is it's hard to know what the real effect sizes are, because once if you do a study, you get an activation region. You've already selected that region based on it having an effect, and so you've overestimated the effect size. So what we did was we took the Human Connectome Project task data, a bunch of these different tasks. And the HCP, prior to doing the study, went through and wrote down, like, what are all the regions that they expected to come out for the particular comparisons in these tasks. So we took those, in some sense, pre-registered hypotheses, because they were in a paper that was published before the data came out. We took those regions, and then we combined them with the regions that we got from Neurosynth. So for example, for the motor task, if the HCP paper said we expect activity in putamen, we would take a region of interest, an anatomical region of interest from an atlas for putamen, and then we would intersect that with the results from a Neurosynth search for motor. Pretty gross search, but the idea is to independently find, where are the voxels that you would expect to be turned on for this particular contrast with reasonable confidence. And then we go in and ask across subjects, what's the effect size? So not surprisingly, you see, so this is, on the left is the bold signal change, right? That's how big is the effect within an individual on average. And what you see is that, for some tasks, like for the supplementary motor cortex in a motor task, you've got about 4% signal change. That's about as big as it gets, right? But that's kind of what you'd expect. For a motor task, they should have whopping activation. Some of them, so for example, in the gambling task, the accumbens has about 2%. In the emotion task, the amygdala has about 2%. And so those are, we would think of those as really big effect sizes in terms of the signal change. The question is, how does that translate into effect sizes at the between subject level? So we heard Tal talk yesterday about how there's an additional set of worries here about sort of generalization across items. This is leaving that out and just asking about power to find an average effect of activation in this region across subjects. And what you see is that for most of the contrast, the median power is below 0.5. So for example, for gambling in the accumbens, it's around 0.2, 0.3. For these emotional tasks in the amygdala, I think it's emotional faces, those are around 0.5. For the highest one is the supplementary motor cortex, around 0.7. So basically this is saying that the best you can hope for in fMRI when you have a whopping effect in like the simplest possible motor task is not even as big as the effect that the median study is powered to find. So half of the studies that were published in 2015 were underpowered even to find this. Right, so you might say, well, why does that matter? They're underpowered. That just means that they're less likely to find things if they're there, right? It turns out that the crux of the Ioannidis paper, the why most published research results are false paper, is this. He points out that in addition to a low-powered study reducing your likelihood of finding something if it's there, it also increases the likelihood that if you find something, that thing is false, right? The sort of reductio that I like to use is, let's say that you have 0 power, right? So you have absolutely no power to find any true effects, but your alpha is 0.05, you're still going to find 5% positives. They're all false positives, so that means every positive result you find is false, right? The higher your power, the more likely you are to find true positives, right? And so the ratio of true to false positives goes up. That's what's called the positive predictive value. Does that make sense to everybody? So what the Button paper kind of did some simulations and laid this out and showed, one, that when you have low power, it reduces the likelihood that any particular finding is true. And that depends on how likely you thought the thing was to start with. And also importantly, if you look at the effect sizes that are estimated from those data, you find that the effect sizes are much bigger the lower power you have. And this relates to a point Tal made in his 2008 paper about big effects in little studies. It's exactly the same point, that basically when you're underpowered, the only thing you can find are the whopping effects. And so you're necessarily going to overestimate the size of the effects. So people still say this, which is sort of astounding to me. My result isn't significant, so I need to add more subjects. And so the question is why? What's wrong with that? Does anybody want to hazard a guess as to why one shouldn't do this? Yeah.
Changes your effective p-value.
It changes your effective p-value. So it does that because you can basically imagine that that you have there's no real effect, right? But when you have a small sample, because you might get one outlier that has a really large effect, it can sort of push your p-value into the significant range, right? Whereas if you kept collecting subjects, it would get pulled back down. But if you're stopping at every subject and doing a test, you're basically going to capitalize on chance, and you're going to end up greatly increasing your false positive rate. This is from a paper, it's the paper titled False Positive Psychology. It's a great paper published a few years ago in Psych Science, which did some simulations and basically showed that, for example, if you start with 10 subjects and then you add one subject and test after each subject, given a nominal p-value of 0.05, your actual false positive rate ends up being 22%. Right? So it greatly inflates the false positives when one does that. So how might we improve this? So power analysis is tricky, and there's tools to do power analysis, but everybody kind of does them without really, I think, believing what comes out of them, because there's so many assumptions that go into them that it's challenging. Nonetheless, I think power analysis is a good thing to do, because we've never done a power analysis for fMRI data that's told us we needed less than about 40 subjects, right? So power analysis is almost always going to tell you need more subjects than you think you need, even if you give it kind of rosy assumptions. So I think it's a good thing to do. And it also is good because it forces you to fix the sample size up front, to write down the sample size. And I think, actually, we'll come back to registration in a bit, because I think that once you've set your sample size up front, it becomes really easy to then go somewhere like Open Science Framework and register it so that it's written down and people know. You can honestly say up front, we set our sample size before ever collecting any data. Any questions so far?
Found a bug in NeuroPower tools when it tells you that you need more than 600 participants. It shows you 600.
But it should just come up with a dialogue that says, please give up now.
You are chasing shadows.
Yeah. Okay, so we all know about the problems with the dimensionality of fMRI, right? But it's fun to play with data just to see how easy it is to fool yourself. So this is if you go to the GitHub, you can actually find the IPython notebook to regenerate this. But basically what I did was I made up fMRI data, right? So I took a mask that's the size of a brain, and I filled it with a bunch of Gaussian random variates. And so basically the idea is that we have a quote-unquote behavioral variable, which is also just Gaussian random noise. And then we have quote-unquote fMRI data for 28 subjects. So the idea is I want to do an analysis that looks for correlation between my quote-unquote behavioral variable and my quote-unquote imaging data, where both of them are completely random. And I click this 2 or 3 times, and I look for the nicest the highest peak, and I do this using a heuristic thresholding technique, right? So I say p less than 0.001, 10 voxel cluster size threshold, which we'll come back to. We now know that that's a really bad thing to do. This is sort of why it's a really bad thing to do, right? Because you will find activation almost every time, and if you plot out that activation, this is like science nature level correlation, right? Of course, it's beautiful, 0.87 from noise, right? So the idea is that, with enough variables, you're going to find some beautiful noise. People in the past, I think, have capitalized on that. Probably, myself included. I think, I should say, and I have a blog post about this recently and ended up in a kind of a Twitter storm. My lab did all these things 10 years ago, right? And, we've learned about how to do things better just as everybody else has, right? So the point here isn't to shame people. I'm as guilty as anybody else. The point here is to, figure out how to do things better. Many of you are probably familiar with the famous salmon paper, which unfortunately gets used in bad ways. But nonetheless, it's funny. I was on the program committee for the human brain mapping meeting when this was submitted as a poster, and it got flagged as a joke initially by some of the reviewers. They said, "Oh, we can't publish this. It's a joke." And we looked at it, and it was like, no, it's actually making a really important point that if you don't do the right corrections, it does it in a humorous way, right? But if you don't do the right corrections, you can find garbage. Okay, so obviously we need to insist on proper corrections, and I think it's becoming clear that the sort of parametric corrections that people have been doing are pretty problematic, and so I think certainly we want to move towards always doing non-parametric corrections, and we can come back and talk about those if there's time. So let's talk about methodological flexibility. So we know that, that even if you just take all the buttons in FSL and sort of combine them factorially, this is an example where we took, at each of these steps of analysis in FSL, took sort of a few reasonable choices. You end up, sorry, this is tiny, that number is 69,120 possible combinations of those. So that's more possible workflows than there are fMRI papers that have been published. Now, obviously, some of those are probably dumb, but a lot of them are, there's no reason that you would intrinsically think that, doing high-pass filter of 100 with 12 motion parameters versus high-pass filter of 120 with 24 parameters, that, one of those is necessarily better than the other. The question is, what happens if you actually look, across all those workflows? So Josh Karp did this. He took one of the data sets from OpenFMRI and ran it through 6,900 workflows, and then looked at how variable things were. Now, this was a data set that we had published. So fortunately, the mean map looks roughly like the story we had told in the paper, so we kind of got lucky with our workflow, I guess. But you also see that the range of statistics across those workflows is pretty huge. So this is the analytic range, and you see that in some regions, the difference between the highest and lowest Z statistic across those workflows is 8. That's a monster difference in Z scores, right? And so that says that you can potentially get huge differences depending on the particular choices you make in your analysis stream. So we've been interested in this in particular in the context of multiple comparison. So we took, for this review this Scanning the Horizon review that I've mentioned, it's actually on bioRxiv if you want to have a look at it. We took the latest 100 papers that just match an fMRI and brain search on PubMed. And of those, 65 reported whole brain activation data. And then we looked in to see what they had done for multiple comparison correction. The good news is that almost everybody did corrected statistics. There's only 3 of those 65 that did not correct. But something funny was going on, and we've informally been seeing this over the last few years, where a number of labs started doing this thing where they'd analyze their data in FSL or SPM, but then use AFNI's AlphaSim to do the multiple comparison correction. And we found that 11% of papers did that. So why is that why would that be a problem? Anybody know why that's a problem? Yeah.
You're cherry picking your method of choosing significance based on the results you're going to see.
Yes.
Well, this is specifically, I think, like received wisdom in labs, right? Like AlphaSim worked better, right? Because there was a
yeah, right.
It was a bug in AlphaSim that often inflated your power. And so people are going to naturally gravitate towards.
Yep. Exactly. So it turned out that alpha-sim was greatly underestimating the cluster size threshold, giving you sort of inflated positive results pretty substantially. And part of this was due to actually a software bug that had to do with masking. Most of it had to do with actually the sort of characterization of the distribution. It turns out that the distributions are longer tailed than a Gaussian. But if you look at sort of the smoothness estimates, you see that AFNI underestimates smoothness, and then these are the cluster size cutoffs. AFNI compared to SPM-FSL, and particularly compared to permutation, underestimated the cutoff for the threshold, which inflated the significance. You can think about this as basically like people in labs looking for the thing that gives them the best results, right? Where in this case, best results may well have been that 0.89 correlation I showed you that's coming from noise.
Can I just ask your experience of that? Which is worse for AFNI, the fact that there was a bug or the fact that there are the long tails?
According to
additive.
Well, I don't know whether they interact. According to Bob Cox, in real situations that aren't sort of simulated data, the bug is a fairly small effect. He claims that the primary effect has to do with the fact that the distributions are longer tailed, and that the nature of the long tailedness is non-stationary across space.
But that's the same problem that's in SPM and FSL as well, or is it instantiated differently?
Yes. Well, yes. So the problem for FSL and SPM, and particularly when you use the lower thresholds, my understanding is that that's also due to the long-tailedness.
Yeah.
Yes. Yep. And it gets worse as the threshold is lower. Yep. So this is another great paper that I would recommend reading called The Garden of Forking Paths by Gelman and Loken, which talks about how, so in the term p-hacking is used in various ways, right? Some people, when they think of p-hacking, they think of a nefarious actor sitting here and saying, I need to find a significant result, right? But in many labs, I think people engage in p-hacking every day without really sort of doing it intentionally, right? They're trying to find a good result, right? They spent hours of their time, thousands of dollars of their PI's research grant, they did a study, and they have to go find something, right? And coming back to the PI and saying, look, nothing came out, is often not, doesn't seem like a viable option. And so people play with things and, try to find results. And so the point that the Gelman and Loken make is that even just kind of, going through data analysis and making data analysis choices that are dependent on what you found in previous steps of data analysis increases your false positive rate, because there's all these possible things you could have done that you're not correcting for. So how do we fix this? So I wrote a blog post last week, a couple weeks ago, about pre-registration and why pre-registration no longer makes me nervous. It used to make me nervous. So how many of you are familiar with the concept of pre-registration? So the idea is, before I ever run a study, I go somewhere, and we've been using the Open Science Framework because that's sort of like come to be the standard place to do this, and you write down, this is what we're going to do. These are how many subjects we're going to collect. These are the hypotheses we're going to test. These are the specific regions of interest we're going to be looking in if we do a small volume correction. What we used to do before we started registering things, we would take a picture of the board where we had written everything down, and I found that useful. But ultimately, it doesn't tell the world that, look, we wrote this down before we collected any data. Now, the main,
I have a quick question about, before you collect any data. Is there, if you, for example, don't look at the outcome, like let's say you've got the clinical population that's continuously collected, can you say all patients that meet these criteria, and we will not look at how many outcomes of either group we have from this date to this date? Is that an equally strong Or is it better to?
I think as long as it's written down beforehand and it doesn't, and the selection criteria don't relate to the outcome that you're measuring, then I think that's a reasonable thing to do. The question is, how do you make sure that the selection criteria don't relate to that outcome? But I think what's most important is just getting rid of any flexibility about how the sample size is selected, what the selection criteria are, inclusion, exclusion, and so on, having that kind of really clearly specified beforehand.
And what do you do if you kind of realize that you made a mistake later? Is it better to kind of stick with what you did? Or?
That's a really good question. I don't know. I mean, I can see arguments both ways, you know. I think that it's probably best to do the best science you can. So like if you do something up front and realize, oh, hey, the thing that we registered is going to give us data that are not useful. You know, we made a mistake in the power analysis, right? And we really need 80 subjects as opposed to 40. If you can say that, you know, this was done without looking at the data, and obviously we have to trust you, but you know, our whole science is based on trust, then I think that's a reasonable thing to do. Go and do another registration and say, hey, look, we made a mistake. You know, we're going to be changing this. This change was based on these criteria, not on the data. And we're currently sort of experimenting with kind of multi-layered registration, where you register what you can, and then, you know, after you've done that, you go back and kind of register the next step. This is an example of something we registered recently that's basically just an analysis project. It's not even a data collection project. It's looking at MRI quality control and basically saying, here's the things that we're going to do. This is the data set we're going to do it on. And then we can always come back and say, now we're going to go, you know, maybe do this on another data set. We have other behavioral stuff where we've registered something saying, we're collecting a data set of this size. You know, part of it's going to be a discovery data set, part's going to be a validation data set. We're not going to touch the validation data set. We're going to do analyses on the discovery set, and then we're going to come back and register the set of analyses that we will go do on the validation set. So those are I mean, I guess I think people think about pre-registration in sort of different ways, and you could think about it in a really kind of inflexible way. I think about it as kind of a way to help us do better science, and so I think that should be the ultimate goal. You know, pre-registration itself shouldn't be like a thing, right? Making the science better should be a thing, and pre-registration should be a tool to help us get there.
So you just would kind of put in your discussion, these are the decisions I made, I registered them here.
Yeah, exactly.
And this is how it morphed over time, and these were why the decisions were made.
Exactly, yeah. Daniel?
I mean, that's one thing that was really interesting to me when I was first wading into the machine learning literature, was the degree to which parameter tuning is just viewed as descriptive and interesting information. Mm-hmm. The frequency with which, particularly if you can quantify the hypothesis space over which you searched on some sort of grid that you can visualize, and most applied machine learning papers in IEEE proceedings won't say we got 86% accuracy, but
right.
we do a heat map that says when lambda was this and gamma was this,
right.
And so you can get a sense of the idea that
Interesting.
on a smooth surface,
right.
Is there a crazy local minimum? And it's much more explicit in terms of here's the space that we searched,
right.
Here's what we found. Maybe people in the future can start searching
right.
this narrow
Interesting.
space, but there's not a claim about that is the most
right.
interesting point on the space. It's a
right.
whole topology.
No, that's cool. Yeah, Luke?
The pre-registration thing, the sentiment I really like, you have to do it so you don't fool yourself.
Yep.
On the other hand, I feel say I had two students, and one of them was I pre-registered my hypothesis, I tested it worked or didn't work. Mm-hmm. And another one said, I didn't pre-register my hypothesis, but here's what I predicted, it didn't work. And I spent the last 6 months trying to figure out why it didn't work. And I went through every assumption I made and all these different things, and I discovered there's a bug in half of them.
Yep.
Isn't that the kind of scientist we want to train?
Yes, but I think you can. It's not an either or there, right?
Yeah, I realize that.
Yeah, no, I think that what should happen is you should, and this is actually getting back to why I was originally nervous about pre-registration. I was nervous because I thought that it would kind of drive people away from interesting discovery science and towards just kind of testing canned hypotheses. And if we only test the hypotheses we know about, we're never going to learn anything new, right? I've become convinced that there's a model And unfortunately, there's not a lot of great examples of this model yet, but a model of a paper that says these were the pre-registered hypotheses we tested, these were the exploratory analyses we did, this is the stuff we found, and potentially this is the replication we did to go, test those. So I think that the point would be that you're going to have more faith in the things that come from the pre-registered analysis than from the discovery analysis, but it doesn't mean that the discovery analysis isn't interesting or publishable. And I think that the field is there's still some confusion about this, and unfortunately, like I said, we don't have good examples. I'm hoping that we and maybe others here will start publishing papers in the next couple of years that will provide examples of that sort of approach. So I think another improvement, you've already have you heard about NiPipe? Okay. Oh, you're going to. Okay, so you will hear about NiPipe. NiPipe is a way for, sort of building workflows and importantly tracking everything that you did, right? So as part of our center, one of the things that we want to do is provide people with the way, as you saw in the demo yesterday, if you were there, you can go do as many analyses as you want, but we're going to track every analysis you do. So ultimately you can say, how many analyses did it take to get to this particular place? This also gives you, really nice tools to do things like trying a bunch of different workflows and then quantify. Obviously you don't want to try a bunch of workflows and take the one that worked best, but what you might want to do, which I think is actually a really important thing to do, is do a number of what seem like reasonable workflows and ask how consistent the results are across them, right? If the results are not consistent, then you might want to be worried that you're sort of capitalizing on a particular thing, or you might want to actually dig in and figure out what are the features of these data that cause that particular workflow to, if you really believe that it works better, why is it working better? Is it some interaction between the TR and the slice timing correction algorithm, or who knows what? We're also really interested in our center and this is sort of the point there, quantifying what we call vibration of effects, right? So John Ioannidis came up with this idea that you want to know how much do effects bounce around in a particular field, and the way that I like to put this is that one of our goals is to get people to stop thinking about P less than 0.05, or it could be Bayes factor over whatever your favorite number is. Stop thinking about sort of passing that threshold as kind of hitting the jackpot, right? That ultimately what you want to be doing is kind of coming up with answers that are believable and that you have faith are going to replicate in the future, not kind of rolling the dice and hoping that you get double sixes or whatever's good in dice. Okay, so any questions so far? Yeah.
I guess I just had a more general question where you were kind of suggesting that you try different workflows and check across the workflows. Does that introduce multiple comparisons as well? Are you then correcting across the different workflows?
Well, you wouldn't. What you would be asking is, for example, so it could, depending on how you treat it, right? So what we would want to ask is not, what we would want to quantify is, let's say that, in our pre-registered workflow, we see there's activation in the left inferior frontal cortex for a particular contrast. What I would like to do now is run those data through 100 workflows and say, how many of those workflows was that activation present for? If that number is like 99, then I'm happy. If that number is 40, then I'm going to get a little worried. If the number is 1, then I'm really worried, right? Okay. So that's the kind of way I'm thinking. So that doesn't really invoke a multiple comparisons problem at least for that one particular area. Now, it would probably if you start doing it across the brain, because you could capitalize on chance at that level. It's kind of this nested problem.
So I guess you're kind of looking at, so you have kind of this one a priori workflow, and then you're checking across workflows and just looking for consistency, even if it's not less than 0.05.
Yeah. Or you could in principle pre-register the 100 workflow meta workflow and say we're going to look for regions that are present at some particular threshold across some particular proportion of workflows. But obviously you want to do that with workflows that you're pretty sure are good, whereas like the Josh Karp thing, clearly some of those workflows were probably really bad, right? So we're not going to be doing it over thousands, we might be doing it over hundreds, because they're going to require curation. Any other questions? Okay, so software errors. So this guy's Jeffrey Chang. He's like a famous hotshot structural biologist at Scripps. And he had this set of papers in the 2000s, 3 science papers, some PNAS papers and other papers about the structure of this particular ATP binding cassette transporter protein. So they do some kind of crystallography or something and find the structure of these things. He had to retract 3 science papers and a couple of other papers because it turned out that there was an error in the code that they'd gotten from another lab to do part of the analysis due to one sign change. That caused the structures to be totally screwed up. Somebody else went and tried to replicate it, found totally different structures. They dug in. They finally found that something was wrong with the code. This is an example of how a tiny little bug in code can have a big effect. I had an example from my own work a few years ago where we had been doing this kind of between subject cross-validation prediction stuff to try to predict what task is a person doing. And I did it and I got 93% accuracy. It's like awesome. Really well, because chance here was like 5%. It was like a 1 out of 20 something prediction problem. We were writing it up this was for the OpenFMRI paper, actually. We were writing it up, and my postdoc Sanmead, I had him do a code review, and he's like, yeah, you did something wrong here. You forgot to properly index these things, and so it actually wasn't slicing the arrays in the way that I thought it was. It didn't crash or anything, right? It actually gave me really good results, but when I reran it, the results they were still significant because they're still much above 0.05, but now we're at 53 rather than 90 something, right? And usually if I see 90 something % accuracy on anything, I get worried that I've done something wrong, right? And I should have here, and I didn't worry enough. But yeah, it turns out that a tiny little error like that, which you wouldn't necessarily catch and is not going to cause a crash, can still cause big changes. This is a great example that came out recently where there was this paper on conspiracy theorists, and basically they had made some claims about the relationship with age that they said age turned out not to correlate with any indicator variables, and it turned out that they had 2 age outliers in their data set, one 32,000 years old. So had they done something really obvious like this, right, they would have found that and figured it out, and probably saved themselves a lot of headache, right? So I think, has anybody talked about testing yet? Okay, so you've heard about testing. Obviously there's a lot of there's a lot of ways one can do testing, right? And I think you can go overboard in testing the wrong things. I think what's important is testing the things that, if they went wrong, would be really problematic. Now, so I wrote a blog recently about this idea of the principle of assumed error, right? And what the blog laid out was the point that in computational research, it's really common to kind of try a lot of stuff, right? And when you find something that works, you stop. Right? And so it's exactly like p-hacking, except it's computational rather than sort of having to do with data collection. And so the principle of assumed error is basically whenever you find a quote-unquote good result, which is one that you're basically the result you're looking for, so like good prediction accuracy on out of sample subjects, assume that you screwed something up. And this is kind of a general or a specific version of Richard Feynman's principle that you just try not to fool yourself. Right? And we should do everything we can to sort of prevent ourselves from fooling ourselves. So sometimes, simple testing approaches are really useful, but other times, you're not going to find something, you're not going to find kind of a really complex algorithmic bug, usually via a smoke test or a unit test. So a couple of the ideas that we try to implement are, one, parameter recovery, right? And this is really relevant when you've written some sort of code to estimate something from data, right? So you want to, for example, estimate the learning rate from a reinforcement learning model. the first thing you should do is generate some data, using independent code, generate some data via a data generation process where you know what the answer should be, adding some realistic noise, perhaps, but probably starting with very little or no noise, and asking whether your code can recover the parameters that it should be able to recover. And we've seen cases, just recently a paper published in one of the top psychology journals making a bunch of claims on the basis of some complicated behavioral models. We got the data from them and found that for most reasonable parameter ranges, their model could not recover the parameters from simulated data. And so it's, this isn't necessarily something that everybody does. Another is randomization. This is more relevant in cases like our classifier training testing thing. It's certainly not a panacea, and in fact, it didn't find problems with the analysis that I showed you earlier. The idea here is basically randomize, sort of break some sort of important relationship in the data, keeping the distributions of the data constant, right, but breaking some important relationships. So for example, if you're trying to predict behavior from imaging, if you have a bunch of unrelated subjects, you can just randomize the ordering of the behavioral labels and then make sure that when you do that a bunch of times, the average relationship is what it should be under chance, under the null hypothesis. The idea is you're basically making the null hypothesis true and then making sure that the results come out. Now you have to do this on the entire workflow, right? You can't do this on just part. So you really want to have this be at the very outside of the entire workflow, because if there's some sort of peaking on the inside, but you're doing your randomization within that peaking, you're still going to see things, but this isn't going to tell you there's a problem. So it's really good to think about upfront before you ever start analyzing the data, what is your strategy going to be for doing these kind of tests? Because that'll make it a lot easier than to figure out exactly how to implement them. Questions about that? Yeah, Aaron.
I thought I'd take I think the example with the age helps us maybe make a little technical distinction between software testing and coding defensive.
Yep.
Right, where if they had tested that with reasonable parameter ranges, the code would have worked just fine without that assertion.
Right.
But putting in that assertion makes them code defensively in a way. So it's like, once you discover that that is a thing that can happen in the world, you put it in there so that your code doesn't just fail silently.
Yeah. So I think you're exactly right. I mean, it's worth thinking about for any on the data side, for whatever data you're working with, you want to think about how can I defend myself from problems in those data? Yeah. So I think defensive program is a good way to put it. Any other questions? All right. So another problem is that we often just have no idea what people did in a paper. How are we on time, by the way? I guess we're good. So in that review that I talked about, where we went through and looked at how people had done their analyses, we found that for about a third of the papers that had done multiple comparison procedure, we could not tell exactly what they had done. They said vague things like cluster-based correction with FSL. We don't know what particular method they used or any other details about it. And so many of you have probably heard about the Kobidas report, which came out recently. There's a paper that is going to be in Nature Neuroscience in the coming months that will sort of lay this out as well. That basically the Kobidas report lays out, what all do you need to report in an imaging study, and says, these are mandatory, these are sort of suggested, these are optional. One of the things that we're sort of excited about and hope will happen is there's tools that are being generated now. So like there's an idea from Yolanda Gill at USC called data narratives, where the idea is that once you have a workflow that's, in their case, that's annotated using a specific provenance model, you can basically automatically generate a methods section at various levels of detail. You can get the nature summary level of detail, you can get the full-on, super detail version. And I think that, ultimately, it doesn't really make sense for us to be, when our workflows are all computational, we shouldn't be writing the methods section, right? The computer should be writing the methods section. It knows what we did much better than we do. Obviously, you can only take that so far. But that's the general idea, is that we should allow the computer to actually do that for us. you've all heard about data sharing and why it's the most awesome thing on earth. And you're going to hear more about BID, so I'm actually not going to say much about it, other than that it's, a great thing. I think that so data sharing is interesting, right? Because there's very little incentive right now for people to share data. It's extra work, it's a pain. You potentially open yourself up to somebody coming along and saying, hey, look, you did this wrong, or hey, look, I analyzed it a different way and the results don't hold up. So there's a lot of risk and a lot of cost without much potential benefit, apparently. But I think that the field is, and particularly I think your generation of scientists, I think my cohort still, a lot of them kind of grumble at me that why do you want us to share our data? It's a pain in the ass. But I get the feeling from talking to grad students and postdocs in our department and at conferences that there's a kind of an increasing realization that sharing data and openness is a good thing. And this is a cool finding that kind of fits with the idea that the people who are sharing data are the people who are doing better science. So they went to a particular psychology journal issue or set of issues and requested data from a bunch of people, and they got back data from like roughly half of them. And then they went through and looked at each paper and used this software that Jelte Vickers has to quantify statistical errors in the paper, and saw that basically the people who had shared their data made fewer errors in their paper than the people who had refused to share their data. And so the hope is that the world will come to see that people who share data are actually doing better science, or at least it could be a lever towards helping you do better science as well. Yeah.
You said that when you speak to people of your generation, that they say that it's a pain in the ass to share data. I think that's definitely a common answer, but do you also find that people want to keep their data because there's more analyses that they can do? So, which do you think is the biggest reason why people it's mostly pain in the ass?
I think pain in the ass is a good cover story, right? I think ultimately it's about you're right, not basically losing the ability to do everything that could be done with the data. I think it's also defensiveness, right? It's thinking, well, I don't know if my grad student actually did that analysis correctly. What if somebody else comes along and shows that our Nature paper was wrong? I think that those are probably the bigger, deeper reasons.
But it's able to say out loud.
Yeah, right. So the things that people say out loud are, one, it's a whole lot of work, or two, oh, I'm worried about subject confidentiality. And right, there are potential reasons to be worried about subject confidentiality, but generally that's just kind of a BS answer that people are using to get you out of their way. Anything else? Yeah.
Is there a practice of publication embargo when you share your data and say you can embargo publication for this long, like 2 years or whatever?
Yeah. So what we're going to be doing, so in the center of the new website that we're building that Chris showed yesterday, the idea will be that anybody who comes on and uses that site has to agree to share their data in the future, because we're giving them free computing and free storage, right? But they will have the ability to embargo the data for some amount of time. That's fairly standard in data sharing across lots of different domains. It's a hard question to know what the right amount of time is. I think 6 months or a year is probably about as long as we want to go in terms of letting people kind of sit on data. But I think that's a totally reasonable thing to do. Yeah.
I think there's a really nice way that pre-registration and embargoing can be linked. Right? There's a way, in some ways, in which that if you collect the data and you pre-register a hypothesis,
right,
particularly if you do pre-review,
right,
you get to lay claim to the specific hypotheses on which the data was collected, and other people who want to do exploratory secondary analyses can still sign an affidavit saying this is the way they analyze the data, right? But I think that there's a really nice way to couple those two issues that address a lot of the concerns of the researchers, while not requiring us to wait a year for people to do cool science.
Right. Yeah. No, I think that's a really good point. There's an interesting experiment that's going to be happening. So there's I don't know how many of you have heard of the ABCD study, this adolescent brain child development study, which is going to be scanning thousands of people, thousands of kids longitudinally, and across a bunch of different sites. And they've agreed to basically set up, it's not going to be required, but it will be basically the default that you have to do a little bit of work to not do, to basically, if you want to get your hands on the data, you're going to be highly sort of the default is going to be to register your hypotheses first on Open Science Framework. And so, one of my frustrations with the Human Connectome project, I was on the external advisory board, and I pushed hard for them to do something like that to try to get people to have a mechanism for people to basically say, here's what I'm going to go do with the data before I grab it, right? Because I have, the HCP data are awesome, right? There's all kinds of stuff that's being done with them that's great. But I also have the worry that, there's a lot of people who are just taking those data and torturing them until they find something, and we're going to have a lot of papers that come from that data set that are just noise, right? And so that's, I think that it'll be interesting to see how this goes with the ABCD. There's not actually a lot of, apparently there's not a lot of great examples of this kind of like for like large-scale shared data kind of pre-registration. I know they have it in some of the like economics and political science data sets.
So the NBA is now following that same approach.
Oh, cool.
It made it actually hard for mathematicians to get hold of the data because they kind of went the flip side and says, what's the scientific research you're doing before we give you access to the data?
Oh, interesting.
And if you said, I'm just going to develop tools, that's something that was outside their scope of possible.
Yeah, see, I think that's probably going too far, right? Cameron, speaking for Indy.
How do you prevent the line from being crossed?
I think that I don't think you can prevent the line from being crossed. I think that what this is about, it's exactly like what I was talking about earlier. It's about nudging people, right? It's about nudging them to pre-register and think a bit about what they're going to do. Obviously, there are some people out in the world who just want to take data. They just want big data to go do stuff with, and if we know that up front, I think that's fine. We just factor that in when they publish it.
But it's so close to get to the point where people are making essentially, forcing you to comply with their opinion of what good science is.
Yeah, this isn't about, so I certainly I would never want the science to be vetted. So like, ADNI, you have to kind of tell them what science you want to do and they have to agree with it, and then they're going to be co-authors and stuff, right? I think that goes way too far, but I think what you do want to do is push people to at least write down up front what it is they want to go do, and then again, when they publish it, they can say, we pre-registered this, right? So we'll have more faith in it than some other lab that just takes the data and publishes a bunch of papers with it, right? I don't think that there's any way to sort of, and I don't think we want to kind of enforce these things. I think we want to think about it in terms of nudges and choice architecture rather than sort of rules and regulations.
Yeah, and it's also, I think it's sort of like the preprint idea. It's a formal record of your integrity.
Yep.
This is what I meant to do, and that's what I found.
Yep.
And I believe that.
Yep.
Well, I see like no reason that you can't, like, if you're just forced to go on record and refer to it and publish, there's like no reason you can't pre-register that, like, I'm going on a fishing expedition.
Yeah, exactly.
Right? And I'm going to do discovery science.
Yep.
And any results that I generate should be taken with an enormous grain of salt.
Right.
And that's what I'm going to do. Because I want to generate a hypothesis.
Right. Or, but you can also think that you do that, and then you write down a little bit about what are our standard operating procedures for parameter search? What are our standard operating procedures for following up results or trying to validate things? I mean, one way that there was a thing I saw on Twitter a while ago about this lab that has sort of like written down all of its standard operating procedures, and I think that's a really good way to start. It's like, just how do we do stuff? What's our strategy, and so on. Yeah. Chris.
It's also important to distinguish that from other practices that are happening out there in certain databases where it is required from people applying to gain access to describe their research.
Right.
But often this description and those plans are being used to gatekeep, basically.
Right. Yeah.
Figure out who I want to share my data with,
Yep.
and who's actually is overlapping too much,
Yep.
to the extent that he's competition.
Yep.
Some databases actually have explicit procedures to gain exclusive access to a part of a data set, to a particular group. And then they want to make sure that a different group doesn't want to do the same research on that subset of data.
Right.
Because obviously, the more people they look at the same data, the worse the data gets. When we present these ideas of pre-registration, we have to make sure that those two will not be conflicted.
Yeah. No, that's why I try to talk about it in terms of sort of nudges. Yeah. Cameron.
So if you are pursuing a hypothesis that's been pre-registered by somebody else, and whether your own hypothesis is registered or not, is it ethical to continue to pursue that? Is part of the idea of pre-registration the idea that other people back off? Is it like calling?
No, not necessarily, I don't think. because the pre-registration doesn't even have to be public, right? Like, you know, I have a postdoc right now who's he basically pre-registers every behavioral study he does, but he keeps them on OSF. You can keep it like private for, I think, 4 years or something like that. And the idea is that it's really more about making him, you know, kind of think clearly and write things down before he does the study, rather than necessarily kind of staking claim for a hypothesis. But I think this is a challenge that we have to think about. How do we deal with it as a scientific society?
So you were saying that for the incentive towards data sharing, it seems like it would be a way to try to call, you know, dibs on this area.
Right.
And it's just interesting because, too, how do you deal with the conflict where you have somebody with a pre-registration and yet, you know, and two people, you know, publishing around the same time?
Yeah.
I don't know. It's just really interesting.
I mean, I don't think it necessarily has to be, you know, the way that we do it now, right, is everybody has their ideas hidden away. They're, you know, cranking on data, the HCP or whatever, right, and they're writing their papers. It wouldn't have to be any different than that, except for the fact that they wrote down before they got the data what they wanted to do, so that when they go to publish, they can expose the hypotheses, right? They don't have to know about they don't have to have any knowledge that other people are doing the same things, right? So in a sense, it doesn't change anything, I think. Yeah.
Has there ever been dialogue, I suppose, on the pre-registration? Because in a way, like if you have this data set you've been collecting for 10 years, you have kind of one shot of unregistered thing, maybe you don't have great experience in half of what you're trying to do, and if someone else is reading it, they're like, wow, that's an awesome data set.
Right.
As a community, we want this to be done well.
Yeah.
I'd like to suggest this.
Right.
Is that?
That's an interesting question. I don't know of any forums where that kind of stuff is happening. It may well be, but I mean, this does raise an interesting issue about data sharing and registration. So one of the other arguments that people make about why they don't want to share their data is, which sort of dovetails with the wanting to, you know, continue to torture the data for years, is look, I spent the last 15 years of my life collecting this really unique data set. I should be able to mine it for the rest of my life. And you know, it's hard to know. Clearly, you want people to be incentivized to do really interesting, cool science. And telling people you have to share your data immediately after all of it immediately after it's published will potentially disincentivize people from doing that. But it might, I think it also might just be that we're not looking at, you know, we have a particular lens on how science works, which is this, like, you know, the person in the ivory tower who spends their 15 years collecting this really unique data set and then kind of lives off it for the rest of their life. I think that there are probably models where that person collects those data, makes them public, and actually benefits even more. But the problem is, I think we don't have good examples of that model.
So someone was talking about having a like you get the paper reviewed before you do the experiment.
Yep.
Is that, I mean, as I guess I haven't heard about that much, or
Right.
I guess high impact or prevalent. That's kind of a way to get feedback on the method from other people who can still do something.
So those are referred to as registered reports, right? And they're generally not in super high impact journals. I don't know what the biggest journals are that are doing it, but you know, none of the big ones. Nature has talked about starting to do something like this, though I think that'll be probably for like really big, important studies that cost millions of dollars, and not for, you know, an imaging study. But I think that's it's an interesting point. And an interesting way to think about doing stuff. We haven't done, so we haven't tried to do any registered reports yet. Has anybody here done one? What was your experience like?
Well, so we were, it was our paradigm that was replicated.
Oh, okay.
This is the psych science ego depletion.
Oh, right. Yeah. Oh, I didn't realize that was you, Kessler.
Yes. So I developed all the stimuli in the analysis package.
Right.
And it was an interesting process. Mm-hmm. It's very different than, I think some of us get spoiled working in interpreted languages where you just get used to, you write, you see the output, you write the code, you see the output. Right. So writing like an R package to defensively program, to think of all of the weird ways that participants would fail the task in ways that were anticipated, that would break the parser. Finding ways to extend the task into Dutch, into Indonesian, into Ukrainian was a really interesting challenge. And ultimately, I think the results are interesting and informative, and I think we know more about ego depletion now than we did when we started. Right. But it was an interesting experience.
That's cool. Let's see. Right. So the other, so we've talked about scooping a bit. I love these are both great quotes, I think. The thing that matters most is being ignored, right? I know of one case of somebody who claims to have been scooped based on shared data, and when you dig into it, it's not quite as clear as their simple story. And so I think that, in practice, it just doesn't really happen. Even though it's at the forefront of everybody's mind. And particularly, obviously you're a trainee, you have this one shot at doing a big study maybe, and if you get scooped on it, that could potentially be a problem. Though for the kind of studies that people in this room do and the kind of work that we do, it's pretty rare for somebody to scoop you in the sense of doing exactly the same thing that you would have done, right? And kind of what it will do is make it so that you can't publish your paper in Nature, right? You have to publish it in Journal of Neuroscience or somewhere, moderate impact. I understand that people want to have Nature papers, but I think that publishing a set of papers that are good and solid is probably is still a good way to have a very solid career without having I know people who've gotten jobs at places like Stanford without Nature and Science papers. So let's see, how much time do we have left? We have 15 minutes left. Okay, so I like this quote by David Donahoe that an article about computational research is advertising, not scholarship, right? That what we really need is kind of the full package of how the data were generated. So I have a story that I like to tell. Many of you are probably familiar with the myconectome study where I scanned myself for a year and a half and then did a bunch of analyses. And I had done all these funky time series analyses using this R package called Forecast. Done them all here on my Mac, and had a package, had everything packaged up, and was going to share all the code. So I wanted to make sure that it would just run on another machine. So I put it onto one of the Linux systems at the Supercomputing Center and ran it. And after a little bit of a few hours of installing packages and stuff, it ran. And I looked at the results, and they were like substantially different. And it turned out that it was like a really tricky bug in that Forecast package, such that the results differed on Linux versus Mac or Windows. So Mac or Windows, I had already had somebody else test it on Windows, and they replicated my results, but on Linux it looked different. And it turned out that it had to do with whether the Y variable was scaled and some other factor that I can't remember. But basically it was this really tricky bug that only happened in certain circumstances on one operating system. That got me really worried. So that's why we started thinking about, instead of just giving out kind of code, which I had done before, actually giving out a full platform. So the way that we did it for that project was making a virtual machine. And I still, have we talked about Docker? Yeah. Okay, so I haven't really moved my workflows over to Docker. I'm still a little more comfortable with virtual machines just because they kind of fit better with how I think about things. But what we did was we set up a virtual machine that could basically pull down all the data, run all the analyses, and then actually put up a web interface running off the VM that you could actually use to explore the data, which is exactly the same web interface you see if you go to results.myconectome.org. And so that was our way of kind of dealing with this irreproducibility issue. And obviously, VMs are heavyweight and probably not the best way to do everything. But I think if you want to give people, it sort of depends on what the use case is, right? If you want to give people tools that they can use to do reproducible analysis, then I think containers are probably the way to go. If you want to give them an entire environment where they can see what's going on and kind of dig around with the data, then something like a VM might be a better way to go. I won't talk about Docker. You're going to hear more about BIDS apps. Okay, so in conclusion, I hope I've convinced you of, most importantly, of a way to think about what we're doing here, right? We're trying to give people tools to help them do better science, right? And to incentivize the things that we want them to do and to disincentivize the things we don't want them to do. And so there's going to be a cost to this, right? There's going to be a lot of grad students who spend several years of their life doing a big study and come to their PI and say, I'm sorry, I have no results from this study. And that's going to have to be an okay thing, right? Because if every study we do results in a paper, then that means that we're either really screwing things up, or we're doing really uninteresting science, right? Because if a lot of the stuff we do doesn't fail, that means that we're not really trying very hard at doing interesting science. But that sucks for the people who it fails for. But we have to. I think the problem is that we currently live in an ecosystem where having a study that fails is viewed as sort of a personal failure, where really we should view failed studies and successful studies as equal in telling us, kind of something about how the world works. And so it requires a change in how the whole world of science thinks about what studies tell us, and that's a much more challenging thing to do. Yeah, Luke?
I don't know if this is a good solution for that, but like what Chris did, where you write up a data paper for it. So the only paper you get is that you're thinking.
Yep.
Someone else wants to get something out of it.
Yeah, no, I think that's a really good point. And I think we also probably need to allow people to publish null results more easily, assuming that the problem is that often now, you get a null result and you don't know if it's because your study has 30% power to find something, or because that something really isn't there. And so once we have better powered studies, we can probably have more faith in the null results. Chris?
So in terms of doing the boring kind of type of science, try to replicate things or new incentives, but it's still not the sexiest thing.
Yep.
I wonder, what are the limits of us trying to change the culture of doing science? Because it is intrinsically more exciting to look at new stuff.
Yep.
Than trying to figure out if an idea is true or not. It's like
humans like shiny things.
Humans like shiny things. People want software developers, not software developers in test. So, what do you think? Do you have any opinion on that? And what's the limit of this? And how can we? Because there's this boring stuff that doesn't happen. How can we make it happen?
Yeah, I can't say I have any good answers in terms of how you incentivize that, other than, driving people to, I think that part of what you have to do is push it back on the initial author. So like in genetics right now, right? If you want to publish a genetic association study, you generally have to replicate that result in another data set before it's publishable in like Nature Genetics or somewhere like that, right? And one thing that does is it gives you author lists of 127 people, right? Which are, as you know, makes writing papers really fun. But I think that might be part of what it takes, is that we're probably, as I say here, we're going to do less. Well, I say we have fewer successes. I think there's also just going to be, if we do it right, there's probably going to be less science. But hopefully it'll be better science, and the likelihood of it actually telling us something useful, either positive or negative, will be higher, right? So I think that you can't just, I think it's wrong to think about it as like there being the discoverers and the replicators, right? That I think we have to figure out a way to make everybody be both of those. And that's I think genomics has done that, reasonably well, at least in the context of genetic association studies. Yeah.
Funding agencies receptive to things that would have to change in order to use these as our best practices, like larger sample sizes, saying that we're now correcting the curve, we're now calculating power appropriately. Are they coming back and saying, well, no, do this with your subjects, we don't want to fund this?
So it's not so much, so the people in the funding agencies are all over this stuff, right? So when you can imagine what their life is like when something comes out that says, thousands of imaging studies are flawed, right? And the program officer who funded a bunch of those imaging studies gets a call from the head of NIH saying, what the fuck, dude? Why are you giving a bunch of money to people to do studies that are wrong? And so they're all over this. The harder part, I think, is the review panels, right? Because they're a bunch of people of my cohort, increasingly younger, but a lot of them my cohort and older, who haven't quite drunk the Kool-Aid and kind of bought into this. And that can make it challenging to get the stuff passed, because they're, the people at least at NIH, the program officers can't just say, we like this, we want to fund it, right? It has to get good reviews. And that's the harder part, I see. But I think they've, and NIH just had in fact, I'm on one of the study sections, and for the first time for this coming meeting, we got a thing basically saying rigor and transparency will be an official review criterion starting, in this particular cycle. And NIH has been, if you watch like their blogs, they've been writing a lot about these things. So they care deeply about this stuff.
And I think some of the connectome projects that are coming out that have been funded. So these have been funded. The data collection, just like the ABCD project, is getting underway right now.
Yep.
So the next 2 years, at least 2,000, if not more, subjects worth of data will be prospectively deposited in the NDA, which means that people should follow these things in terms of the hypothesis that they could test without even collecting a new data set. And I think that's going to perhaps shift things around.
But I think for the large data sets, this culture of being open sort of it's a little bit better than the more traditional, I'm going to do this study, I'm designing a paradigm, it's small, it's at my institution, and so I'm thinking, how do those of us who still have, 1 foot there, and that's kind of our primary discipline, how do we help to get our science, using the best practices, but also get it funded?
Yeah, I think it's definitely a challenge, and so basically you have to go to NIH and ask them for either twice as much money to do the same amount of science or the same amount of money to do half the science, and the only hope for that is that that rigor and transparency criterion becomes important enough that people will see it and say, well, they aren't claiming to do as much as this other grant, but we have faith that they're going to do it in a way that we can really believe. They're just going to give us answers that we believe, as opposed to this other one. But I agree. It's a challenge. Yeah. Luke?
What's your opinion about, if, let's say there was a software bug discovered in acne, and SPM always one. It's like lots of studies. Should everybody retract their papers?
No, because the fact that there's a bug doesn't necessarily tell us that those are all false positives, right? They tell us that the false positive rate is higher than you might hope. What I think they should have done in the first place is deposited their data in OpenFMRI so somebody could come along and reanalyze imagine if you could go back and reanalyze all those 40,000 studies that were mentioned in the Eklund paper, right? And actually know what's the updated false positive rate, right? And then it might be the case that, I have to go back and retract some of my papers that I did in a dumb way with SPM in 2001 or whatever. And I would be perfectly willing to do that if it were shown that, reanalyzing those data, that the conclusions failed to hold up.
Why I bring it up is I feel like, if you get really deep in this, you're like, of course it's wrong, we should do it. And the current state of science is all previous states of science should reflect the current state, which seems crazy, right?
Right.
But on the other hand, you don't want to have findings in literature that are proven to be or shown to be wrong.
Right. Well, it's even harder, right? Because even when you retract something, for the most part, people continue to cite the original one as true, right? Retractions have very little impact on ultimate usage of the citation. So it's hard to know how to do that. But I don't think that bug would necessarily.
And I mentioned
right.
But like with the science papers, in my time, if it's clearly wrong, I feel like that was a very that was
Yeah, it's different. For something like that, it's clearly wrong, right? For statistical stuff, it's it's probabilistically wrong.
So sort of a similar question, as a grad student, you've been talking a lot about nudging people to share code and data and stuff. What about managing that fear that you were talking about earlier, which is, say somebody discovers something, so you put your code up online, there's a problem in the paper that you published or something like that, and maybe you're lucky enough that it gets some attention initially, and now you have this issue where you're afraid people criticizing your work, and there's a shame culture that forms around that.
Yep.
Oh God, I'm doing a job.
Yep.
This is stupid. I shouldn't have shared anything in the first place. The scientific group that is stuck out there, right?
Yeah.
How do you manage that?
Yeah, no, I think it's really tough. I think.
There's a lot of shared sentiment.
Yeah.
It's like everyone in this room is like on the same page about this,
Yeah,
right? But
right.
the people that you want to get to do this stuff
Yeah.
have legit fears about this.
Yeah, yeah. Well, so it depends on what mood I'm in. I mean, one answer that I might give, and I don't know if this is a satisfying answer, is basically that, well, if you can't get a job doing the science the way that you want to do it, then maybe you don't want to be in this world anyway, right? And you can go get a job for Facebook or Google, right?
Where do we go?
I think anybody in this room could get a job at Facebook or Uber or Google or wherever. But no, that's totally legit, and that's my cynical answer, right? I guess my non-cynical what would my non-cynical answer be?
I feel hopeful about the fact that the funding agencies are so on this.
Yeah.
I think a lot of people have been saying for the last 10 years, they've been making the moral arguments, but the funding at the beginning of the pipeline and the reward structure in terms of publishing the journals at the end of the pipeline,
right.
they are starting to become on board. And I think when I go to events in the UK, and I think it's similar in the US, when you speak with the funders, they're really big on it. For exactly the reason that you said before. And that is my personal role.
Yeah, but that doesn't address the shame culture that you mentioned, which I think is a huge problem, right? That there's at least a subset of people who view, problems in code or, failure of replication or whatever else as as at best a personal failure, at worst fraud, right? And I think that's a really problematic kind of dynamic that has emerged, at least in a subset of people around the replication thing. You may want to speak to that directly.
I mean, so just pragmatically, right? So you talk about sort of the different generations of scientists. Is this the sort of thing that the liberalization of a lot of social views in the West just takes time for generations to die off?
Some of you may know that there's a famous quote that's attributed to various people like Henry Kissinger, that's not a Henry Kissinger, it's forget who it is. Science progresses one funeral at a time.
Yeah. Right.
And I think there's no, it's interesting. There's actually data showing that when a famous person dies, the people who worked with them in the period following that, their productivity goes down, and people who worked for others in the same field, their productivity goes up. So it really does progress one funeral at a time.
I could just comment on that. So as a grad student, you're out starting kind of the shame culture. It's a lot more risky and shameful if you spend 5 years of your life and then publish this, and now someone's going to comment on it. At the greater, everybody doesn't even get to pipe in on your method until you've invested potentially 5 years.
Yep.
So in a way, it seems like the structure should be reversed, in which right now, before I've publish something, I'm much more comfortable with someone saying, I think that your method may not be great, or you made an error here, or this or that, because it's not quite as. So in a way, it seems like we should be commenting as a community on the planned method, and that would be less.
Yeah, and I think that becomes increasingly important as the stuff that we do becomes so interdisciplinary, right? Where in principle, that's the job of your dissertation committee, right, to help give you that advice. But often your dissertation committee is not going to have people with deep expertise in all the things that are important for your particular work, and so getting more feedback like that. And I don't know what the right mechanism is for that. Clearly, registered replication or registered reports are one of those.
You could like it or comment or.
Right. You could. You can write a blog, right, and get your friends to comment on it there. The question is, how do you actually get the people you want commenting on it to comment? And the problem is that it's I would love to be able to comment on everybody's studies in here, but I hardly have time to comment on the work of the people in my own lab, right?
Russ, let's since it's 10:30, let's kind of hear and take more discussion over coffee. So let's do.
Cool.
How are we doing on time, Sandra? So if you take 15 minutes, is that? Yeah. So let's take 15 minutes. There's coffee upstairs. Continue the discussion there, and then come back down here in 15 minutes.
Standing ovation.